This is predator-prey interaction from observed behavior to direct measure. This presentation will be an overview on different methods used to infer whether or not acoustically tagged fish have encountered a predator, and also some methods on directly measuring predation events. This is movement and habitat use of Chinook salmon, smolts, and northern pike minnow during day and night cycles to exemplify the relative distribution of predators and prey. During the day, smolts concentrate along shore and under the bridge, shown here, possibly seeking cover from predators. Pike minnow concentrate in a few localized areas. At night, there are low concentrations of smolt, and data points for predators were spread out over a large area, including areas offshore outside the coverage area of the hydrophone array. Acoustic telemetry methods have also been routinely used to monitor predatory fish movement, behavior, and travel time. The photo on the left shows alligator gar being tagged, and the photo on the right indicates the travel path after release in the hydrophone array. This particular tracking was done as part of a National Geographic television special about tracking alligator gar in the Trinity River in Texas. Use of acoustic tagging systems requires certain assumptions. Steps are taken to mitigate using tag burden rules, tag size, and shape criteria, using standardized surgical procedures, and use of non-toxic materials. Many controlled tests have been conducted to confirm basic assumptions are met. That the tag has not been eaten is not under control in the natural environment. We usually don't have the opportunity to see these interactions in the natural environment, but there are clues in acoustic tag data that can indicate certain behaviors. These next few slides will show the behaviors we have observed using the HTI acoustic telemetry system graphical interface software, both in the raw data and in the analyzed data from the 2D, 3D tracks. Then we will show more examples of the direct measure of predation using the PDAT predatory tag. To be able to understand these behaviors, we need to back up a bit to our company origins in hydroacoustics. Hydroacoustics uses a transducer which transmits a short sound pulse into the water and waits listening for echoes to return, repeating this cycle many times every second. Those familiar with hydroacoustics will recognize the echogram on the left. Shown is the hydroacoustic survey result of a transducer listening within some water body with the reflections from the organisms throughout the water column and the bottom track in yellow. Time is the horizontal axis and depth is the vertical axis. On the right is the HTI acoustic tag system graphical interface. You might see a resemblance because when we made it, we simply took the transmitter out of the transducer and put it in a tag. The graphic on the right shows acoustic tag survey, the result of a hydrophone listening. The patterns of paired horizontal and diagonal lines are tag transmissions. Here, transmissions received at separate hydrophones are colored accordingly. For example, green to green, blue to blue, pink to pink, and yellow to yellow. The raw data here shows transmissions getting closer and then farther away from each hydrophone. This information is then combined to create a track that the tagged fish took. Now onto methods for inferring predation events. Here are 3 separate tags tracked by a single hydrophone over some time period. You'll note that the pattern of moving towards and away the hydrophone is exactly the same for all 3 of these tags. This is a strong indication that all 3 of these tags have been predated by the same fish. Because of digestion, at some point the results of predation will be tag defecation. The data on the left indicates movement toward and away from several different hydrophones. The returns from individual hydrophones are shown in different colors. The orange hydrophone, the green hydrophone, the yellow hydrophone, all in different locations and varying distances from the tag at any time. Using the graphical interface with the raw data files will allow observation of the exact timing of tag defecation. Here is the same pattern of defecation with a single hydrophone detection. You'll note that there are 2 tags here in the same time period traveling together. Then at a defecation event, one tag remains stationary while the other continues swimming off. Here is that same defecation event detected across multiple hydrophones. Again, different hydrophones have different color. Now we take the raw data and put it in a real-world context using the post-processed 2D tracking. This is an overview of the tracking done on a tagged striped bass in red and a tagged, dead, fed to the striped bass Chinook in blue. Initially, the tagged salmon is separate from the striped bass while it's deployed. After the predator has consumed its prey, simultaneous tag tracks in the salmon and striped bass are observed. The simultaneous tag tracking in the striped bass and the salmon continues for almost 2 days. It is then followed by an evacuation event, where the striped bass continues moving and the Chinook remains in place. Here the striped bass continues, while the Chinook remains in place, having been defecated. Here is another overview of observed predatory behavior shown in 2D tracking. The green is a steelhead, and the striped bass is red. Upstream to downstream goes from the bottom right to the top left of this picture, with a barrier in the middle. Initially, the steelhead approaches from upstream. We observe that it is migrating until it reaches the boundary. It then proceeds to search for a path through, and once it finds this path, continues its migration. You'll note that the red here, indicating the predator, has been stationary this entire time. In fact, for nearly 2 full days, that tag remained stationary, and it was assumed that it had been defecated. However, once the steelhead reaches the predator begins to move. We see predator avoidance behavior in the steelhead, and the predator is now actively searching for prey. You'll note that the hydrophone array here, shown with colored dots, does not extend all the way to where the predator and prey are now. It is unknown in this instance, because of their position outside of the hydrophone array, whether or not a predation event has occurred. Here is yet another example of predator-prey tracking. 2 Chinook tags enter this array individually from upstream, the top right of this picture. Tags begin swimming simultaneously and continue to do so for 3+ days. One tag is defecated and remains in the array, while the other leaves the array back upstream. This is strong evidence that both tags were predated by the same fish. Another indication of predator behavior is tortuosity. The top row here shows radial movement of predatory fish, and the bottom shows radial movement of salmon smolt. The complete track of each fish was broken up into line segments of approximately 10 seconds in duration, and the direction of travel of each segment was then calculated and summarized in the above plots. You'll note that the smolts have a much narrower focus of direction than the predators do. The tracking data that went into those radial plots are shown here. This is of the predator fish, and this is of the smolts. Clearly, each of these groups exhibits different swimming behavior. Now we move from an indication of predatory behavior to a method where we can measure the behavior directly. Pit tags and acoustic tags from tagged smolts are routinely located in Caspian tern detritus on islands at the mouth of the Columbian River. The acoustic tag tracked fish behavior, and the pit tag was later detected in the nesting areas around the Columbian River basin. The tag is helping to better quantify avian salmonid consumption and is helping reveal the impact of the predator-prey dynamic. Here is an acoustic pit tag, Composite, designed for avian predation studies. Pit tag integration into acoustic tag adds about 0.1 gram weight to the acoustic tag. However, there is need for a tag that can identify an acoustic tagged fish that has been eaten by a non-avian predator. In 2013, HTI developed a prototype Predation Tag, similar in size, shape, and weight to normal acoustic tags used for juvenile salmon. In recent years, as more data has become available for various species via fine-scale 2D and 3D telemetry, new questions have emerged. One of the principal questions of great importance is, can we determine whether or not an acoustically tagged fish has been eaten by a predator? A critical assumption of survival estimates for acoustically tagged migrating species is that the detected tag signals are from distinctly unconsumed and freely migrating fish. With these questions, HTI set out to create a tool that directly measures predation. Thus began the design and engineering of HTI's Predation Tag. This new tool will directly measure predation via a unique modification in the acoustic tag signal. HTI's Predation Tag has been in laboratory testing, is patent pending in the United States and Canada, and has had positive results being deployed in the field. Here again is the raw data visualization tool used by HTI to track tags in a hydrophone array. However, this is a predation tag and has a different signal before and after a predation event has occurred. HTI would be happy to answer questions on our Facebook page, our LinkedIn profile, via email, or over the phone. Thank you for listening to this presentation.